This is group 5. In this video, we will talk all about combinational circuit. This video will cover combinational circuit, of course, then full adder circuits, well, rather half adder first, then full adder. So, let's jump into the combinational circuit first.
Hi, my name is Alexander Nsmandap. I'm here to discuss about combinational circuits. So what is combinational circuits? A combinational circuit comprises of logical gates whose output at any time are determined directly from the present combination of inputs without any regards to previous inputs. It performs a specific information processing operation fully specified logically by a set of Boolean functions. Basic components of our combinational circuits are input variables, logic gates, and output variables. The n inputs variables comes from a external source, whereas the n output variables goes to external destination. In many applications, the source or destination are stored registers.
Hello guys, I'm Michael Manangkaya. In this lesson, uh, we're going to discuss the combinational circuit. It is the continuation of introduction of combinational circuit. So, output is dependent upon combination of input variables. So, generally, combinational circuit is the circuit whose the output will depend upon the input variables. As the name indicates, the output of the combinational circuit will depend upon the combinational input variables. Given, generally, this is the logic circuit, which is having the different logic gates in integrating the combinational circuit. Doesn't use any memory. It is upon the input combination, and it is not going to depend upon the any previous state input circuit. It cannot affect the output. It can have n number of inputs and m number of outputs. Adders and subtractors. The best example of combinational circuit, adders and subtractors. Adders and subtractors are fundamentals component of combinational circuits used in arithmetic operations. Decoders which decodes input into output. Multiplexers is a combinational circuit that selects one of many input signals and forwards the selected input to a single output line. Code converters are combinational circuits used to convert data from one binary code format to another. Comparators. It is combinational circuit that compares two binary numbers and outputs their relationships. Read-only memory, programmable logic array, and programmable array logics. These examples of combinational circuits. Thank you.
So hello guys, my name is Arvin Ken Imangale, and today I am presenting to you combinational logic circuits. Let's explore various combinational logic circuits. Let's go. Right. So in this discussion, we explored various combinational logic circuits utilizing different types of gates, including OR gates, AND gates, NOT gates, NAND gates, and NOR gates. Here's a breakdown of the key concepts and Boolean expressions derived from the circuits. So let's discuss OR gate. OR gate produces an output of true, 1, if at least one input is true. Example, for inputs A and B, the output is A or B, Boolean representation. Let's present that here. So A is equal, A and B If it passes the OR gate, then it will be A or B. Yes, guys, this reads as A or B when it passes the OR gate. So let's go to the next. AND gate. So let's discuss AND gate. AND gate produces an output of true only if both inputs are true. Example, for inputs C and D, the output is C and D. That's the output and what? That's the output for when the inputs that's the output when the input passes through a AND gate. So let's proceed. Now let's discuss NOT gate. So NOT gate inverts the input value. For example, if the input is A or B, the output is A or B NOTed. So let's show that real quick. So A or B or A plus B. This reads as OR, the plus sign. Then the output will be A or B NOTed. This is the NOT sign. So let's proceed now. Now, complex combinations. Circuits can combine multiple gates, leading to more complex Boolean expressions. For instance, if an OR gate combines the output of two AND gates, the overall output is F is equal to A and B or A and B. So I'm gonna explain here real quick. So AND gate and the input of the AND gate is A and B. And the downside, the input is A and B. So when it passes to the OR gate converts it into a, what do you call this, an OR sign. So plus sign means it is an OR. So the final answer is F is equal to A and B or A and B. I don't know how to read it correctly though, but this is the right, this is the right, this is the right explanation for this. At least in my studies. So next. So let's discuss NAND gate. NAND gate combines AND operation followed by NOT. For example, for inputs A and B, the output is A and B, knotted. So knotted means there's a, I guess let's call it underscore at the top. So that shows that this is a NAND gate. This circuit logic board is the NAND gate. So let's proceed to another. Oops. So this is the NOR gate. So NOR gate, as you can see, this is the NOR gate, and let's discuss the NOR gate. NOR gate combines OR operation followed by NOT. For example, for inputs C and D, let's put C and D. C and D, the output will be C or D knotted. So you notice that NOR and OR gate must have the same values, but let's take it apart. Let's look it up in the next discussion. So we could decide what's the difference between OR and NOR gate. Now, expression derivation. Analyze each gate sequentially. So you can derive each of the gate and write down the right formula for it. So write the Boolean representation based on inputs and the type of gate. So this is what you call analyze each gate sequentially. So you can present it at the right gate and the right type of the formula. So combine, excuse me. So combine outputs as necessary to create final expression for the circuit. So each gate has some formula into it. So you have to derive each and everything so you can get the right answer. So let's proceed. In conclusion, understanding relationships between inputs and outputs in combinational logic circuits is essential for designing and analyzing digital systems. By using Boolean algebra, one can effectively derive expressions that represent the logical functionality of these circuits. This knowledge is foundational for anyone studying digital electronics and computer engineering. Thank you all for listening. So, thank you.
Hi, my name is Gerald A. Nagutom. I'm here to report the gates of combination. We're going to start off with this gate here, which is a two-input OR gate. The output F for this gate is F equals the Euling of the inputs A and B. So that expression is F equals A or B. If we come to this gate here, which is the AND gate, the expression of the output is F equals A and B. This gate, which is one input NOT gate, and in fact, you can only have one input to a NOT gate. The output is F equals NOT A. If we look at this gate, which is a two-input NOR gate, then the output expression here is F equals A or B, all noted. This case is an example of a NAND gate, and the output here is F equals A and B, all noted. Let's have A go at the first example here, which is saying F is A, and we've noted again. Now, essentially, what we're trying to achieve here is a combinational logic circuit here, F equals not A, because this is very important in one logic. Next, let's have a look at this building expression here and see if we can reproduce this with a combinational logic circuit. Let's start by writing the expression out again. Here we can see F is equal to A and B, or A and not B. What's important is that we build up the logic circuit a little bit time. So I'm going to look at this area of the overall Boyle expression, which is A and B. We put a little loop there, which means this is connected to B input, and you come down here and that's input. What you have here is A not B, because the output of the NOT gates would be A not B. Now the output here will be not B, because the A and the not B are the inputs to the particular AND gate. Now let's come down here and draw this out. Input, we'll have look at the input. We have A and B, and the other input is A and not B. So here I have A and B being one of the inputs now, because this is an OR gate. This will be an OR symbol here, and it will be ordered with the other input, which is produce the combinational logic circuit for this particular Boylen expression here.
Hi, I'm Maria Francesca Aragadio. I'm going to have my input A and my input B. We're going to take those inputs through A and get a two input and gate. So let me carefully draw that here, and the output of that is going to be A and B. Now the other expression is going to be produced by a two input or gate. So this is my two input or gate. And what I wanted, the output is now A or B. Again, this expression here now to achieve that, I know my input is going to be A not A, and the other input is going to have VAB. So at this position here, I will have the not A, and the other input is B. So I'm going to tap off that B. I'm going to come down here and input that to the other input of these two input or gate. Then now both of these outputs are going to go through an AND gate. That noted, which implies A and B gate. What doesn't imply it is A and B gate, and that's because we have this band across the top here, and we have this, and as you can, F will now equal its inputs here. One of the inputs here are A and B. The other inputs is this one here, not A or B, and to emphasize, they're both separate inputs. I put them in brackets, and of course, this gate A is A and B get. So what it's going to do, it's going to end them and then not lot, and we can say that this is expression we were trying to produce right at the very beginning. So we've just produced a combinational logic circuit for that particular building expression.
Half adder. A half adder is a combination circuit that adds two bits producing a sum and a carry output. Basically, a half adder is a basic circuit used in digital electronics that helps add two binary numbers. It's called a half adder because it doesn't account for carrying in values from previous bits, unlike a full adder. A half adder circuit needs two binary inputs and two binary outputs. Inputs X and Y, augment and addend bits. Output sum bit S and carry bit C.
Truth table. X and Y are the two inputs. Two inputs is X and Y, and two output is carry and sesam. The carry output is 0 unless both the inputs are 1. 0 plus 0, 0 output. 0 plus 1, sa carry 0, sa sum is 1. 1 plus 0, 0 sa carry, sum is 1. 1 plus 1, carry naman ang magiging 1, then si sum is magiging 0.
Here in my presentation, I will discuss how do we get the expression of half-ager and the logic diagram for half-ager circuit. So, dito muna tayo sa pagkuha natin ng expression of half-ager. So, dito sa half-ager, expression ng half-ager, meron tayong dalawang kima, which is the kima for sum and kima for carry. So, dito sa kima for sum, meron tayong output na dalawang 1, which is ito lang, dito sa sum natin. So, yung value ni y is 1. Then, yung value ni x is 1. So, dito makakabuo tayo ng expression na not x and y, then x not y. So, yung not x is nagre-represent siya na yung x natin is equal siya sa 0. Same with din sa y natin dito. Since 0 to, then yung y natin is not. So, makakabuo tayo ng expression sa sum na not xy plus x not y. So, in Boolean algebra, pwede natin gawin siyang yung sum natin is x or y. So, dito, nakabuo tayo ng expression kay sum. So, dito naman tayo kay carry. Bubuo tayo ng expression kay carry. So, paano nga ba natin nakuha yun? So, dito sa kima for carry. So, sa wait lang, burahin ko lang tong yan. So, dito naman sa carry, yung output natin is isang 1 lang. So, yung gagamitin natin is ito lang. So, yung value ni x is 1, value ni y is 1. So, dito maglalagay natin yung 1. So, since yung x natin is nag-value sa 1, ganyan. Makabuo tayo ng xy sa expression, which kaya natin nabuo tong expression na c is equal to xy. So, nakabuo na tayo ng expression. Dito naman tayo sa punta naman tayo dito sa logic diagram for half-ager circuit. So, paano nga ba natin nabuo tong diagram na to? So, dito sa expression natin, meron tayong sa S, nakabuo tayo ng expression na X or Y. Kaya naglagay ako dito ng XOR gate. Ito, XOR gate. XOR gate. So, dito sa XOR, ano ba yung XOR? Only if 1, the input is 1. So, mag-output lang daw siya ng 1 kung yung dalawang output niya is merong 1. So, dito sa example natin is maglalagay tayo ng input na 1. So, ayan. Since may input tayo na 1 na isa, mag-i-input siya, mag-output siya ng 1. So, paano naman kapag dalawang 1? Mag-output siya ng 0. since if both the input is 1 or both the input is 0, the output is 0. So, kahit gawin natin siyang 0 is mag-output pa rin siya ng 0. So, dito naman sa AND gate, since sa expression natin nakabuo tayong expression na x, y, x and y. So, kaya naglagay ako dito ng AND gate. So, ano ba yung AND gate? If both input are 1, the output is 1. So, yung output daw niya is magiging 1 lang kapag yung parehong input niya is 1. So, dito, maglalagay ako ng input na 1 na pareho. So, ayan, yung output niya is naging 1. So, paano naman kapag dalawang 0? Is yung output niya is maging 1 lang dahil magiging 1 lang daw yung output niya is kapag yung parehong input niya is 1. Yan. Kahit yung isang 1 siya, magiging 0 pa din siya. So, yun lang po.
Para naman po sa basic operation, sa half-adder we have two binary inputs which we will refer as A and B. Example, iset po natin yung dalawang input sa 0, so ang output ay magiging 0 din. Bali, meron po tayong dalawang inputs, sum S and the pair C. So when we add A and B, sum S equals A plus B equals 0 plus 0 equals 0. Since both inputs are 0, ang result po ng addition is also 0. Next naman po, hanapin natin yung carry output. Nag-generate lang po ang carry kapag both inputs are 1. So, carry C equals A and B equals 0 and 0 is equals to 0. Since wala pong input na 1, both ang result niya ay no carry generated. So, ang basic operation of a half-adder demonstrates a fundamental role in binary addition.
Meron tayong truth table dito na may two single bit binary numbers, tapos dalawang output. Tapos ito yung logical representation natin or logic diagram. Tapos ito yung ginamit natin na expression ng half-adder para makuha yung outputs ng each content. Sa logical diagram naman makikita natin yung mga inputs saka yung outputs. Ito. Example na lang natin yung first row ng contents nila. Si X ay may 1, tapos si Y naman ay may 0. Sa XOR, kahit sa isang 1 lang dito sa dalawang inputs natin, tulad dito sa third row na may 1 din siya. Ang magiging output niya ay 1 ang sum at 0 si carry. Kahit magkapalit yan, magiging 1 pa rin si sum tapos 0 si carry. Dito naman sa second row, wala silang 1 kahit isa. So magiging output nila ay pares lang din na 0. Dito naman sa AND gate, makikita natin na dalawa sila may 1 sa inputs nila. Ang magiging magiging output nila, si carry yung may 1 at si sum naman yung may 0. Kasi yung kay XOR, dapat isa lang. Kahit sa input, basta isang 1 lang, tapos yung isa na iba. Para maging 1 at 0 ang mga output nila. Ganyan.
Is lesson 3, full adder circuit.
Full adder circuit. This circuit needs 3 binary inputs and 2 binary outputs. This mostly happens when each of 2 binary inputs, X and Y, has 2 or more bits when being added together. In layman's term, it adds 3 bits together, 2 bits from numbers you want to add, and 1 bit that comes from previous addition carried, called the carry. It gives you two results, sum, the result of the addition, and a new carry bit. If there is a value that needs to be carried over the next addition, think of it like a calculator for bits. Full adder truth table. This table shows all the possible combination of binary inputs and outputs in full adder circuit. Two of the input variable x and y present the two significant bits to be added. The third input variable z presents the carry from the previous lower significant position. And the outputs are designed by the symbol S for summary and Z for carry. So this is the example of the truth table. If x is 0 and y is 0, the carry from the previous lower significant position is 0. Uh, the output will be uh, carry for 0 and sum for 0. Next, if x is 0 and y is 0, the carry from the previous lower significant position is 1. The output will be 0 for carry and 1 for sum. Next is if x is 0 and y is 1, the carry from the previous lower significant is 0, and the output will be 0 for carry and 1 for sum. Next is if x is 0 and y is 0, the
What?
carry from the previous lower significant position is 1. The output will be 1 for carry and 0 for sum. Next, if x is 1 and y is 0, the carry from the previous lower significant position is 0. The output will be c for carry and 1 for sum. Next, if x is 1 and y is 0, the carry from the previous lower significant is 1. The carry will be 1 and the sum is 0. Next, if x is 1 and y is 1, the carry from the previous lower significant position is 0. The output will be 1 for carry and 0 for sum. Next, if one is x and y is 1, the carry from the previous lower significant position is 1. The output will be 1 for carry and 1 for sum.
So we will now proceed to the maps for a full adder circuit. Now, let's start first making the K map for the sum. Ngayon, karoon tayo ng input dito, i-base natin sa truth table. Hanapin natin yung may 1 sa sum, which is x and y is equal to 0 and z is equal to 1. But x and y, x is equal to 0, y is equal to 1, x and z is equal to 0. Y is equal to 1. X is equal to 1. YZ is equal to 0. X equal to 1. YZ equal to 0. So, XYZ is equal to 1. So, we derive with this formula. Ay, paano siya kunin? Nag-base din tayo dito sa mga may 1. First, we start with ito, x not, y, bakit not? Kasi 0 yung value nila. X not, then y is equal to 0. So y not, z. Kasi siya yung nag-hold ng 1. So x not, y not, z plus x not, ito naman, x not is equal to 0. Y not is equal, hindi pala y not, y lang siya. Kasi siya pala yung nag-hold ng 1, then z not, siya yung 0. X equal to x, y not, 0 siya. G not, 0. Plus x, y, z. Kasi parehas silang may 1. So, this is the equation for this sum. Now, we should proceed. So, K-map naman ng carry. Gaya ng ginawa natin sa sum, hinanap muna natin sa table yung may 1 sa sum. Pero dito sa carry, mag-base naman tayo sa carry. So, tingnan natin. 1 siya. X equal to 0, yz is equal to 1. Ito. Yz 1, 0, x. X1, 0. X1, 0. Here, ito. 0. Okay. Xy is equal to 1, z is equal to ito. Then pinakalas. XYZ is equal to 1. Ngayon, as you can see, nakabilog siya. It means, i-group natin siya. Group natin. We will find the common group. Ngayon, may tatlo tayong group. Isang isang vertical, dalawang horizontal. Ngayon, unahin natin ito horizontal. This one. Ano yung common sa kanila? Similar. Which is x. Just nandito sila sa x-axis. And then, yung value is 1. Yung y. So, tingnan natin i-derive to. xy, x, plus xz. Check natin. Plus xz. Ito. Ito siya. X common, nasa x-axis. And then yung z, ayun yung v1. Xy plus xz. Ngayon, itong last plus yz. Ito. Nasa yz yung v1. So, ngayon, na-derive na natin yung equation ng sum tsaka carry. Ita-transpose na natin sila into the diagram using logical gates. Logic diagram for whole other circuit. So, ito na equation na derive natin kanina for the sum. X naught here, this is the left. Then y naught. Then the z. Here. Kumbaga short short diagram siya, full adder. Naintindihan dito, pero medyo complicated lang. Let's say, ano to, X, Y, and then Z. Ano yung una kaninang term? X naught here, and then Y naught. X here, then Z. I mean, diretso na wala na. Then, second term, X naught, Y Z naught. X naught here, dito na siya kumonect. Ay, ito pala. X naught. And then Y. So, bago mag-naught, bumaba na siya. Then sa Z naught here. Ito, naught. Dito, and so on. So forth. Then, let's proceed dito sa carry. Carrying equation. C is equal to X to Y plus X and Z. Diba? X and Y. X is here. X. Then Y. X. Then, wala siyang dire-diretso. Ayun. This is the logic diagram. Ngayon, I suggest if you're studying circuit, you can use this website, Circuitverse. Mas interactive siya. Mas ma-explore nyo yung circuit. Ngayon, verify lang natin kung tama ba tong diagram na na-derive natin using itong sum and carry na map. Let's say Z is equal to 1. Dapat yung sum is 1. Yeah. Dapat nakachamba lang. X 1. That is okay. 1 X Z. Therefore, conclude tama tama. So now that you know yung formula and then yung diagram, we should now proceed sa example.
Making sense of the full adder circuit. First, to understand the full adder circuit, we must first understand what a half adder is. It was discussed in the previous topic that was in this video. And from there, we know that if we add 0 and 0 together, the answer will be sum is 0 and the carry will be 0. If we add 1 and 0 together, if either x is 1, y is 0, or x is 0 and y is 1, the sum will be 1 and the carry will be 0. And if x and y are both 1, if we add them together, the sum will be 0 and the carry will be 1. But that only applies if there's only one bit. What if each binary input comes with 2 bits or even more? That's where the full adder circuit comes in. Example, here we have an example. X will be equivalent to 1, 0, and the y will be equivalent to 1, 1. Now, to add this, we must first go back to what we understood back in our elementary days. we add that first the digit from the rightmost part of the number. Here, we add the rightmost bit of the binary input because we're now talking about bits. Okay. So first, what are the rightmost bit? It's 0 and 1. And as you can see, the formula is the same as the half adder circuit because we're only performing half adder for the rightmost bit of the addition. Okay, so our x will be equal to 0 and our y will be equal to 1. And as we know from before, from the half adder circuit, 0 and 1 added together, the sum will be 1 and the carry will be 0. Now, this carry will be, well, carried on to the next significant position of the addition, which will be the left bit of the bit that we just added, which in this case, x will be equal to 1 and y will be equal to 1. And as we know, z will be the carry from the previous lower significant position. And what was the carry from the previous lower significant position in our case? That is 0, as we can see from the example. So now we have the three inputs that we need. X will be 1, y will be 1, and the z will be equal to 0. And as we know from before that was discussed in the truth table, we know that if x is 1, y is 1, and the z or the carry from the previous lower significant position is 0, the answer will be sum will be 0 and the carry will be 1. So therefore, the final answer for this is, it's not written here, it's 1, 0, 1. That is the answer. So as you can see, the full adder circuit part of the input outputs the same bits as the one in the truth table, like in just said. So now we go to the examples.
Example number 1. X is equal to 1101 and y is equal to 0111. First bit, 1 plus 1 is equal to 0, carry 1. First bit, sum is 0, carry 1, half adder. Next, 1 plus 0 plus 1 is equal to 0, carry out 1. Second bit, sum is 0, carry 1, full adder. Next, 1 plus 1 is equal to 1, carry out 1. Third bit, sum is 1, carry out 1, full adder. Next, 1 plus 1 plus 0 is equal to 0, carry out 1. In fourth bit, sum is 0, carry out 1, full adder. Lastly, 1 plus 0 equals 1. In fifth bit, sum is 1, carry out 0, full adder. And the final answer is 10100.
Example 2. X is equals to 1011, which has a decimal number of 11, and Y is equals to 0001, which has a decimal number of 1. 1 plus 1 is equals to 0, carry out 1. First bit, sum is equals to 0, carry is equals to 1, half adder. Next is 1 plus 1 plus 0 is equals to 0, carry out 1. Second bit, sum is equals to 0, carry is 1, full adder. Next is 1 plus 0 is equals to 1, carry 0. Third bit, sum is equals to 1, carry is 0, full adder. And the last is 0 plus 1 plus 0 is equals to 1, carry 0. Fourth bit, sum is equals to 1, carry is 0, full adder. And our final output is 1100, which has a decimal number of 12.
And that's it for group 5. Thank you so much for watching.